Okay, welcome back. We're continuing a development of the density of states function. Last time we concluded from our particle in a box that the number of states per volume in K space is a cubed over pi cubed, or the regular physical volume over pi cubed. So that's our delta VK. It's 1 over delta VK. So that would be our differential volume per state in K space. So the number of states per volume, per unit volume in K space is kind of the first piece of the puzzle that we did last time. Now we want to see what is the differential volume in K space as a function of K. We're looking for the number of states per unit volume. So let's consider this. We ended up with this sketch last time. We have two spheres, one of radius k, one of radius k plus dk. Only these are eighth of a sphere. So simply the volume here in K space, I'm going to call it V sub k, to indicate that it is the volume in K space. And it's a function of K. So the volume in K space is a function of K. Well, it's for a given value of K, it's 4/3 pi times the radius, which is here K, cubed. So that's the volume of a sphere of radius K. But we only have 1/8 of the sphere, because we're only in the quadrant where all the K values are positive, or all the Kx, Ky values are positive. So we have to divide by 8 for 1/8 of our sphere. So this gives us, of course, 1/6 pi K cubed as the volume for a given K in K space. Well, how do we find the differential volume? One way is to say I've got this volume for one sphere, and we subtract it from the volume of the larger value of K. We can do that, and then you note that higher orders of this differential go to 0. Or we can just take the derivative with respect to K. So let's do that. We take the derivative with respect to K. dvk dk is 3/6 pi k squared. So this is 1/2 pi k squared. And we have dv sub k, or differential volume, is 1/2 pi k squared dk. Our differential volume in K space, dv sub k, is equal to 1/2 pi k squared dk. So that is, geometrically, the volume of this shell. The shell of thickness dk, and its radius out here is k. Now we can put these two pieces together and find the number of states per unit volume per unit K space volume. That's not quite what we're after at the end, but we're getting there. So we got two pieces of the puzzle. This was part number 2. So we're looking for we're looking for the number of states per unit volume in regular space per unit volume in K space. And this is going to be g of k dk Well, the per unit volume here, we're just going to say 1 over V. The number per unit volume, the differential volume in K space, we just found to be pi over 2 K squared dk. So this is our differential volume in K space. And then we have the number of states per unit volume in K space. This is what we found first. This is the number of states per unit volume in K space. This gives our differential volume in K space. So this is going to give us the number of states per differential volume in K space. And this would be it, except that the Pauli exclusion principle says that there's actually, we do have 2 spin states for electrons. So we actually end up getting, or actually it's not really the Pauli exclusion principle, but there are 2 spin states. The Pauli exclusion principle will then say that at that point you can only have no more than one particle in a state, but we have 2 spin states. So we're multiplying times 2 for spin right here. All right, so we're dividing by the physical volume, so we get it per unit physical volume. Here's the differential volume for a given value of K, and here's the number of states per unit volume in K space. And we do a little bit of algebra here, and just, let's see here, we've got a pi canceled there, we get volume cancels, kind of nice there. We have 2 canceling with 2 there, and we get G of K dk is equal to K squared over pi squared dk. All right, so we're making progress. We're definitely making progress. However, this is in terms of K, of wave number, and we want it in terms of energy. Well, we get to then go back and say, recall that for a free particle, remember this is a free particle we're developing this for. For a free particle, energy is equal to h bar squared k squared over 2m. So K is equal to the square root of 2me over h bar. All right, so going back to our EK relationship for a free particle, we can relate E and K. I'm going to go back up here now. And so I can take the derivative of this with respect to K, I get, and then multiply back over by dk. dE is equal to 2h bar squared k over 2m dk. 2's cancel, and I can say that I can rearrange a little bit and note that k dk is equal to m over h bar squared dE. Okay, so I see here that I've got k squared dk. I've got an expression for k in terms of E. Now I've got an expression for k dk in terms of E, well, and dE. So I can substitute in here for k dk and here for k, and I find that pi squared one of these K's is my 2me over h bar. That's K, and then my KdK is m over h bar squared dE. I'm going to simplify this a little bit, but we kind of ponder this. Here's our 1 over pi squared. We've got our K and our KdK. I've got a square root of E. I've got square root of 2m. I've got an m. All right. And if I express, now I also recall that h bar is equal to h over 2 pi. So if I do a little more simplification and get this in terms of h instead of h bar, I can find that g of k dk is equal to g of e dE is equal to 1 over pi squared, square root of 2me over h bar, m over h bar squared dE is kind of what I've got right there. And I'm going to go back up here. I don't really want the dE's. I can cancel out the dE's and get my g of E function, my density of states function. And so here I've got, right here, I've got h over 2 pi cubed. That's going to cancel. There's going to be some cancellations of pi's and 2's and everything. So what I get is my density of states function, g of E, is 4 pi 2m to the 3 halves over h cubed, so this is Planck's constant cubed, not h bar, but just Planck's constant, times the square root of E. All right, so this is my density of states function for an electron, a free particle, fermion. We started in a big box, a big cube, and we found we had 3 steps, right? We found the number of states in K space per unit volume in K space, the number of states per unit volume in K space. We found the differential volume in K space for a given value of K, K dK, we had that. And then we put those things together and divided by the volume in physical space to get the number of states per unit volume K space. Had to multiply times 2 for spin, 2 spin states. And then we converted from K to E. So here is our density of states function, G of E. How do we use this in semiconductors? Well, in semiconductors, we will use this in the following way. For electrons in the conduction band, we will modify this a little bit, and we'll have a G sub C for the density of states in the conduction band. It's a function of E. 4 pi 2 and now we'll use the effective mass of electrons in the conduction band. And you notice that this starts with E equals 0 and goes up from 0. Well, we're going to start at the conduction band edge. So this gets modified here as E minus E sub c. So this is the energy above the conduction band energy. Well, that's the net right there. And then, because in the conduction band, E is greater than or equal to the conduction band energy E sub c. And then for holes in the valence band, remember that's going to, the parabola there opens down. So G sub V for valence band, is a function of E. 4 pi, you can imagine we're going to use the effective mass of holes. Right, we've got the effective mass of holes. And instead of going up, we're going to go down from the valence band energy. So instead of E or E minus, we got to have a positive number. It's going to be E sub V minus E, because we're going down in energy. Again, E here is less than or equal to E sub V. And the density of states between the valence band and the conduction band is 0. There are no states between the valence band and the conduction band. That's a forbidden band. All right, so there's our density of states function. It goes as the square root of energy. It's fairly simple, as it turns out. We do have to modify it here with our effective mass of electrons in the conduction band, and we're going from the conduction band edge up, so E minus E sub c. Effective mass for holes in the valence band, and then E sub V minus E as we go down in energy. All right, so there's our density of states function. Next, we will look at the probability of a state being occupied. This is a separate issue from the number of states that exist. We'll do that next.